I guess we should start. So this is the third of series of frontier lectures with the goal to emphasize the achievements of South American mathematicians. So today we are very happy to have Carolina Araujo from IMPA with us, and Carolina is the representative of one of these golden generations of South American mathematicians, including Cola Marquez, Helcott, Lupesio, Uribe, Carolina herself, who won many international prizes in mathematics. And she's also someone with a very special lineage. Her advisor is Pura. So Janos is probably one of the most powerful algebraic geometers today. So, but he is very unique in his training. So, 73, 30, and 74, he was representing Hungary, the oldest Olympiad country in the world. He was representing Hungary at the International Olympiad, and he won first prize in both of these Olympiads. Then he, no matter that he had categories, he actually started with non-commutative algebra and wrote a bunch of papers with Erwin Fried. This tradition in Hungarian mathematics goes back to Janos von Neumann, more known in this country as John von Neumann. But but then when he was in his fourth year, he realized that he can write a paper every week. So that wasn't much of a challenge. So he switched to algebraic geometry, and he never went back. But so he started in Soviet Union in Moscow at that time under the Iskovsky and Shakurov, and then he went to graduate school in Brandeis and then Matsusaka. Brandeis is rather close to Harvard. So he combines in his training all these three schools. There, of course, he's in Princeton and enhance his algebraic geometry society with very fine products like Carolina Araujo. So first, let me thank you for coming and welcome you with one of our presents. So we have now new logo of the Institute and t-shirts, here you go, and caps. That's for you. Our sponsor, this is the Stronghold Foundation, who were very nice to sponsor this frontier series in mathematics, and we are working forward to developing this collaboration with others. So I am the representative of the social program. Very interesting topic comes from physics, from general relativity, and of course, it was Eugenio Calabi, who is still alive, turning 100 this year. And Carolina is going to tell us more about this problem, which actually has different appearances in many areas of modern mathematics. Carolina?
Thank you very much, Ludmil, for the very nice introduction. So I'm very happy and very okay, now okay. So So thank you, Ludmil, for the introduction, and I'm very, very honored to be giving this Frontiers lecture. So Ludmil told me that I should prepare my first talk for a general audience, and then so I prepared this talk actually for students. I apologize for the experts, but then you have to wait until tomorrow to learn something a bit more advanced.
Well, we can learn today.
Okay. Anyway, so first of all, let me introduce myself. I'm Carolina Araujo, and I work at INPA. And so here is a map so that you can locate INPA in the globe. And at INPA, I do algebraic geometry. More specifically, I'm specialized in birational geometry. And so this is my point of view mathematically. And also, besides research, I've been involved also I've been serving the Committee for Women in Mathematics of the INU for 8 years now. And so this is another passion of mine. And so today I would like to discuss the Calabi problem from a birational geometer's viewpoint. And so this, as I said, this is really an introductory lecture. So I do not, even though it's different when I prepared this, I did not assume that the audience knew any even geometry. So I will start from the very beginning. And so this is the plan for today. So I will first of all introduce what is algebraic geometry, and then also discuss some aspects of differential geometry, and then discuss some interplays between these two areas, two types of geometry, and culminating with the description of the Calabi problem. And then tomorrow, I will go a little bit deeper into the Calabi problem and then into birational geometry, and explain what are the tools from the birational geometry that have been developed and that have yielded like great progress in the Calabi problem in the last few years. Okay, so let me start with algebraic geometry. So let me tell you what algebraic geometry is, and for that, let me start with this quote from Sir Michael Atiyah. Should you just be an algebraist or a geometer is like saying, would you rather be deaf or blind? In the sense that we have all our senses to perceive the world, and it's good that we use all of them so that we get a better understanding of the world. And this is the same thing for math. We have many mathematical senses that we can use to make progress in this discipline, and it is good if we use all our mathematical senses. So to say what algebraic geometry is, let me first start by discussing geometry in general. So geometry is concerned with properties of geometric properties of the space, such as curvature, shape, size, and it's been originally developed to model the world that we live in. And so let me start. I would like to illustrate this with a very simple example. As I said, it's very introductory. And so let me discuss the ellipse. So as we all know, the ellipse is the curve in the plane consisting, so you have to fix two focal points, and then you take all the points in the plane whose distance to these 2 points add to a fixed given quantity. And now let me explain how we can use this very simple mathematical object and how it has been used to model aspects of the world, and more specifically of planetary motions. And so this is I'm going to explain some of the Kepler's laws. So Kepler was a German astronomer, and he put himself to work on the trajectory, to understand the trajectory of Mars. And he wrote this book in 1609 called The New Astronomy, where he reports the results of his research, and in particular his the two of his three laws of planetary motions. And let me explain them. So the first one says that that a planet, the trajectory of the planet is an ellipse, with the sun being at one of its focal points. And the second Kepler's law explains the velocity of the planet in this orbit. So the velocity is not constant, and it is described in the following way. So it varies constantly in such a way that at the same area is swept out in same intervals of time. So for instance, these two sectors will have the same area, and so that means that even though these distances are different, they are the planet goes around with the same in the same interval of time. Okay, so this with these two laws, he could actually predict and draw the trajectory of Mars. And I'm sure that you all know about Kepler. So I'd like to take this opportunity to introduce you to another great astronomer that is less known, a female astronomer. So this is Maria Konieczka. So she's from Silesia, which is now Poland. And she was the most notable female astronomer of the early modern era. So she was from a very well-educated family, and she did not have any formal education. At that time, it was not very well regarded to let women learn about the natural sciences, but her parents allowed her to embrace her passion for mathematics and astronomy, and she could study, and she learned many things. She spoke 7 languages, was really a remarkable woman. And she worked on Kepler's laws and studied and further developed Kepler's work. And in particular, she developed she got new tables. She fixed some mistakes in Kepler's computations and set up a much better working solution to Kepler's problem. So her work, she published a book in 1650 with her discoveries. Okay, so let me we'll move to algebra. So very roughly speaking, algebra is a study of mathematical symbols and how to manipulate them in a formula. So let me give you a very simple example. So I'm sure that you have all seen the quadratic equation, and it's possible to solve any such equation by manipulating the symbols in this formula. So this is a very well-known Bhaskara formula. And within algebra, there is a very popular field of research, which is the number theory. So there is this quote of Gauss that says that mathematics is the queen of the sciences, and number theory is the queen of mathematics. So number theory studies properties of integers in more general numbers in a more general way. And so one important problem within number theory is to find all the integer solutions of a given polynomial equation, like this one. So this is a very famous one. This for when n is 1 or 2, of course, we have many solutions. So for n equals to 2, the solutions are called the Pythagorean triples, and they were known to the Babylonians. And but there is a very important theorem that for n at least 3, there's no non-trivial solutions to this equation. So this was first stated by Fermat in the margin of his copy of Diophantus' Arithmetics, that this solution does not have, this equation does not have non-trivial solutions for n at least 3. But it was actually proved more than 300 years later. And we will come back to that later on. So now, let me say how these things are put together. So geometry and physics, geometry and algebra can be put together by means of Cartesian coordinates. So every point in the plane can be represented by its coordinates x and y. So this is a very important development in science, and it allows us to connect geometry and algebra. So, for instance, the ellipse that we saw before can be given by this polynomial equation. And in general, algebraic geometry studies solutions of polynomial equations in several variables, and this is where the algebra comes from. And the solutions have a geometric manifestation. So I just put here some algebraic equations, polynomial equations, and their solution set. And so the idea in algebraic geometry is that we either start with an equation and understand the geometric properties of its solution set, or the other way around. You know, sometimes we're interested in algebraic solutions, but we cannot really solve the problem, so we study the geometry to get qualitative information. Okay, so now let me explain a aspect of algebraic geometry, or more precisely projective geometry, that differs from the usual Euclidean geometry. So in Euclidean geometry, we start with some set of axioms. So this should be intuitive or appealing. And then from those, we deduce other results. And among the Euclides axioms, there's the so-called parallel axiom, or the fifth axiom, that says that if you're given a line, well, this is not the original formulation, but it is equivalent to it. If you're given a line and a point outside the line, then you can always, you can draw a unique parallel line to L passing through the point P. So this is known as the parallel axiom, and this is a very interesting chapter of mathematics. So for many decades, mathematicians believe that this axiom could be proved from the other ones, and we're trying to do it until in the 19th century. Finally, mathematicians realized that the fifth axiom was in fact independent of the other ones, because you can construct other types of geometry where the fifth postulate does not hold, and in a consistent way. So you could, there are two ways that you can negate this. You can always say that you can either, there are geometries where you do not have parallel lines, and geometries where you have given a line L and point P, there are infinitely many lines that are parallel to L passing through P. And in projective geometry, basically there are no parallel lines. So projective geometry is born in say perspective drawing, and so in a perspective drawing there are no parallel lines. For instance, if you have two parallel lines, and then if you they will meet, they sort of meet at infinity. So in projective geometry, we will add points to the plane. In the case of the plane, we will add points to the plane by adding one limit point for every direction in the plane. And so now two lines that used to be parallel in the Euclidean world, after we attach this point at infinity, then they meet. And if you have just two other parallel lines, they will meet. So all the parallel lines and the points at infinity lines on the horizon line. And to do this, but in algebraic geometry, we do it in a way that the new points that we add, they are indistinguishable from the old points. So this is the way that we formally define is by introducing the projective plane. So the projective plane we can define as the set of lines passing through the origin. And as you drew here, so if you have coordinates x, y, and z, you can think of your original plane as the plane z equals to 1. And so for every point in the plane, you can join this point to the origin, and then this gives you a line for the origin that is now in the projective plane. And almost all lines are obtained in this way, except for the lines in the plane in the plane z equals to 0. And so now, so these are what I wrote here is just a way to represent the points in the projective plane. So we can represent a point in the projective plane by what we call projective coordinates x, y, and z. So these are the coordinates in R3 of any point lying in the line, any point other than the origin lying in this line. So the only thing we have to be careful here is that we can have different representations for the same point. Basically, any x, y, z will represent the same point in the projective plane and the multiple, non-zero multiple ax, ay, and ways and az. And this gives us a very practical way of computing and working in coordinates in the projective plane. For instance, if I start with this hyperbola, given by this equation x, y equals to 1, then if I imagine that if I add points at infinity, I will be adding points here. We can imagine that we will be once we compactify, when we projectivize the plane, we are going to get two more points on the curve corresponding to the vertical and the horizontal asymptotic directions. And if you work with projective coordinates, you can do this, so you can check this very easily. So let me give you the recipe for this. So if we start with the curve given by a polynomial equation, to get the projective model of it, so first thing you do is you homogenize your polynomial. So the original polynomial was not homogeneous, so we homogenize by adding z to whatever power that is necessary, so that all the terms have the same degree. And now, as I said, the points corresponding, the point at infinity are those corresponding to z coordinate equal to 0. So if we set z equal to 0 here, we get exactly two solutions. These are 2 points of infinity, and these are the points 0, 1, 0, and 1, 0, 0. And this corresponds precisely to these two asymptotic lines. And so this is so we have a very concrete way of working with the projective plane. And now let me give you another example. So now let's consider this curve in the plane in R2 given by this equation. So again, we can, in order to add the points at infinity, we can imagine, we can do the same recipe as before, and then you will see that there is one asymptotic line, which is corresponding to the vertical direction. So once we projectivize this curve, we add this one point, and then the picture that we get can be represented by these two circles in the real projective plane. So this is something like this. But then we can instead of considering only the real solutions to this equation, we could also consider the complex solution. So if we allow for complex solutions, in fact, we get much more solutions. And it turns out that we have a picture that, well, it can be pictured in this way. So if you look at the complex solutions to this polynomial equation, you get something that looks like a torus. So what you should get from this picture is that even if you were interested in real algebraic geometry or real geometry, if you allow for complex points, then you get a much better understanding of the object. So before, it looks like before we were just looking at the section of the source, and once you allow for all the solutions, you have the picture makes much more sense. And in fact, here I just put those two examples. You can look at the solutions in the reals or in the complex numbers. But if you're interested in number theory, then you may want to look at the integer solutions. And because we are in the projective plane, we can rescale. This is the same thing as looking for rational solutions. And if you're interested in applications of algebraic geometry, then you want to get solutions in some finite fields. So this is very important for applications to cryptography, for instance. And then again, you would look at this equation, and then you would look for solutions in a certain finite. And so, and now what I want to discuss now is a very deep revolution that happened in algebraic geometry when Grothendieck realized that, in fact, there is one object. This is what he introduced as a scheme. That is, it's a mathematical object that is associated to the equation. So you can look at the scheme, say, corresponding to this equation, and this scheme carries information of the solutions either over the reals or the complex or the rationals or the or finite fields or whatever base ring or base field you're interested. So and so all these aspects are encoded in the scheme, and they can be and different. Looking at different fields means that you're just looking from different angles at the same object. So let me give this, like very much this quotation from Grothendieck, is that if there is one thing in mathematics that fascinates me more than anything else, it is neither number nor size, but always since this was this theory that allowed Andrew Wiles to finally prove Fermat's theorem in 1995. Okay, so this is about algebraic geometry, and now let me discuss some aspects of differential geometry. So in differential geometry, one often uses tools from differential calculus to understand and to study geometric properties of smooth manifolds. So let me discuss one very important notion in differential geometry, which is that of a curvature. So intuitively, a curvature measures how much a curve deviates from being a straight line. And let me tell you how you can actually formally, one way of defining formally the curvature of a curve is the following. So start, for instance, with this curve C, then and a point P. So I want to define what is the curvature of the curve at the point P. Then I choose there is a best circle that approximates the curve at that point. So this is the circle that I draw there, and this circle has a certain radius. And the curvature can be defined as the inverse of this radius. So if you see that a straight line, we have the circle that best approximates it. It's a circle with radius infinity. So the curvature is 0 of a straight line. While if you have a very, very small circle, so the curvature is very big because the radius is very small. So this is the notion of curvature. There is one also extra information, which is that when you look at your curve, then the circle that best approximates the curve at different points, it can be lies either under the curve or above the curve. And so the curvature of a, say, plane curve or comes with a sign that is just a convention that we choose. And so this gives us the notion of a curvature of a curve in the, say, in the plane. And now let me explain the notion of curvature of a surface as introduced by Gauss. So if you give me a surface in the space and a point in the surface, then if I cut my surface with a is to take the minimum and the maximum curvature that this way and multiply them. And this is what we call the Gaussian curvature of the surface at the point. And for instance, in this case, we would see that the curvature is negative. And as this notion was studied by Gauss, and he proved that this now called the Gaussian curvature is intrinsic. So it does not depend, it only roughly speaking, it can be measured just by if you know how to measure length, it's enough to be able to compute the curvature. So to make this more precise, I need to explain what is a Riemannian geometry. So this is a very powerful language. So basically, a manifold, a Riemannian manifold is a smooth manifold M together with a Riemannian metric. So Riemannian metric is just a product, a positive definite product in a tangent space that varies continuously with the point. So if I have this inner product that varies continuously with the point, I can use it. I have a notion, a local notion of angles and distance, and so I can measure angles and distance, and I can even define the curvature only from this data. And now for surfaces, the curvature defines this sort of this great trichotomy for surfaces, which is a negative curvature, zero curvature, which is and positive curvature. So this is illustrated by these pictures, and also we can define the notion of parallel transport. So what this means is that this is a way to sort of transport the geometry from one point to nearby point. So if you have a curve in your surface, and you have a tangent vector, the parallel transport gives you a way of translating this vector so that it always stays parallel. Okay, so now let me discuss some interplays between the algebraic and differential geometry. So let me start with a projective curve in the plane. So this is usually given by a polynomial, homogeneous polynomial equation like this, and I assume that this the corresponding curve has no singularities, in the sense that let me assume that the partial derivatives of this polynomial do not all vanish at the same point. So if you have this condition, that you can use the implicit function theorem to write down basically one coordinate in terms of the other, and this is in fact, even though we call it a curve, and I write it as C, this is in fact just a Riemann surface. And associated to a Riemann surface, I always have a genus, which is, so every compact Riemann surface is just basically a sphere with a certain number of handles, and this number is the genus of the Riemann surface. And this genus captures a lot of the geometry. In particular, we have the important Gauss-Bonnet theorem that says that the average of the curvature of this Riemann surface is 2 pi times 2 minus 2g. So even though we don't know what is in principle the metric. Just from this topological data, we can have information on the curvature. But now in our case, our reading surface is given by a algebraic equation. And so there is a connection now between the geometry, in this case the genus, and the algebra, and the algebra in this case is just the degree of the polynomial. So this is a formula that we learned in the first class of algebraic geometry. It's called the degree genus formula, that says that from the degree of the polynomial equation, you can read off the genus. And so the great trichotomy for the curvature, in the case of projective plane curves, can be translated into this trichotomy, like genus, very low degree, 1 or 2, degree 3, just zero curvature, and high degree, which is gives a negative curvature. Now, in higher dimensional complex geometry, we can generalize this notion of the genus. And so if you give me a complex projective variety, then I can define what we call the anti-canonical class. This is the first Chern, defined as the first Chern class of the tangent bundle of X. Let me tell you what this is. So this is a cohomology class that again measures curvature. So if you give me any complex curve on X, then I can intersect it with this anti-canonical class, and it gives me the average up to scaling. It gives me the average of the curvature of X along the curve. And so this is what we use. So this will be a higher dimensional generalization of the notion of the genus. And it's called, as I said, the canonical class. The K is called the canonical class of X. And again, in higher dimensional, for higher dimensional projective varieties, we have the trichotomy. Now we have so this is some names for today. So this when the canonical class is positive, then I call it a general type. And when the canonical class is 0, I call it, let me call it Calabian. And when the canonical class is negative, I call it Fermat varieties. So let me give you an example. When my projective variety is given by a single equation, what we call a hypersurface, it has a certain degree, so it's given by a polynomial of degree d, and the canonical class is can be read off from the degree, just like the genus of the Riemann surface was read off from the degree. And then the trichotomy, so the general type, it's really general type because you see its most hypersurfaces are of this form. When the degree is greater or equal than n plus 2, when the degree is exactly n plus 1, then the canonical class is 0, and when the degree is less or equal than n, then the canonical class is negative. And yeah, so I'm assuming that this is a smooth, reducible hypersurface. So this is just to give you an example of the taste of what this is, but there's a warning that in general, the sign of the canonical class is not well defined, in the sense that you will have curves that for which the canonical class is negative with respect to this curve, and others positive and others 0. So there's no definite sign for the canonical class. However, there's this very powerful theory in higher dimensional algebraic geometry, which is called the minimal model program. And it as a consequence of the minimal model program, it turns out that all complex projective varieties can be built up from these 3 classes of varieties. So this is a very deep and important theory in algebraic geometry. So tomorrow in my lecture tomorrow, I will spend some time explaining the minimal model program, but today maybe we can think of this as a sort of a black box that tells us, how a given projective variety can be constructed from varieties in these 3 fundamental classes.
Why do you need to assume complex? What goes wrong with other fields?
Well, so for other fields, there is work being done, but for the complex, this is where the theory is most developed. So, for instance, resolution of singularities is something that we have over the complex, but so far we do not have any positive characteristics. So, so there are some technical tools that at this moment are not available in positive characteristics. But in principle, one expects that you can have, and this is being developed by other people. So I work usually over the complex, but for sure these questions make sense and are studied more generally.
In art is done already. Like
Sorry?
In the real life is done already, not on the complex.
Well, over the real things are big, so I should work over an algebraic closed field. So if you want to work over other fields, it's okay in the sense, okay, first you take the algebraic closure, and then you have a good period there, and then you see what survives when you try to go back. Okay, but I think this is, so tomorrow for sure we will spend more time discussing the minimum model program, but not today. So I think now I would like to move to the Calabi problem and state the Calabi problem. So this is Eugenio Calabi, and in fact, as Eugenio pointed out, he will turn 100 years old next week. And so so this problem was advertised in his ICM talk in 1954, and the problem can be put in this way. So which complex varieties admit a Kähler-Einstein metric? So my goal now is to explain what a Kähler-Einstein metric is. And so let me start with first with the Kähler metrics. So here, let's start with a complex variety, and the Kähler metric is this is given in terms of a complex structure, and the Kähler metric is a Riemannian metric on X that is compatible with the complex structure. So to make this, one way of making this more precise is to say that at every tangent space, you have a linear map which is given by multiplication by I, and I say that the Riemannian metric is compatible with the complex structure when parallel. So first of all, the metric is compatible. It's invariant if I multiply by I at each tangent space, and also that the parallel transform commutes with this complex multiplication. And so this is what a Kähler metric is. And for instance, the projective space admits a Kähler metric. It is the Fubini-Studi metric on the projective space. And if you take any projective variety, so this any variety, a subvariety of the projective space, closed subvariety that's defined by, say, polynomial equations, then you can restrict the Fubini-Studi metric on CPN to X, and this is also, again, Kähler. And now, let me define a Kähler-Einstein metric. So you start already with something that has a Kähler metric, so a compact Kähler variety. And a Kähler-Einstein metric on X is just a Kähler metric with constant curvature. And the Calabi problem asks, so which Kähler varieties admit a Kähler-Einstein metric? And for instance, every Riemann surface admits a unique Kähler-Einstein metric. So this is the consequence of the Poincaré uniformization theorem. And of course, the curvature. So as I said here, the curvature must be constant, and so by rescaling, you can always assume that it's either 1, 0, or -1, and of course the sign of the curvature will depend on the genus. So this is already fixed. So and in this case, if you look, for instance, at the case of curvature 0, the way that I draw it, we think of the torus embedded in R3, then of course it is does not have a constant zero curvature, but we can give it other metrics. For instance, we can think of the torus as a square in the plane with the side identified, and then this gives a flat metric with a constant zero curvature on the torus. And now, okay, so now more generally, which Kähler varieties admit a Kähler-Einstein metric? So let's recall that the canonical class that I introduced, the canonical class of X, and I explained that it measures the curvature of X. So a necessary condition for X to admit a Kähler-Einstein metric is that the sign of the canonical class is well defined. And so we must, so in order for X to admit a Kähler-Einstein metric, it must live in one of these three big classes that I discussed before, that, you know, were the same three classes coming from the minimal model program. And so we can restrict them to, each one of these three big classes of variety and ask the Calabi problem there. So for the first one, so the first result was proved by Yau in 1976. So he proved that if the canonical class is zero, then X always admits a Kähler-Einstein metric. So this is a very important theorem, and it's one of the reasons why Yau got the Fields Medal. And it has also, even though this is I should say that this is very analytic, you know, the methods are very analytic. You have to solve some Monge-Ampère type of equations to produce a Kähler-Einstein metric. Although it, as we will see tomorrow, it has striking consequences even to algebraic geometry. So shortly after that, then Aubin and Yau proved the similar result for manifolds with positive canonical class or negative curvature. So again, if the canonical class is positive, then X always admit a Kähler-Einstein metric. And well, I didn't say it, but Calabi already proved when in his ICM talk that if a Kähler-Einstein metric exists, then it is unique. So this is sort of canonical in some sense. Now, so it remains to look at the third class of varieties, fundamental class of varieties, which is that of funnel manifolds, so canonical class, negative or positive curvature. And now things get much more subtle. So funnel varieties may or may not admit a Kähler-Einstein metric. So this was known from the very beginning. There are examples of funnel varieties without a Kähler-Einstein metric. And so if you're if you're interested in the Calabi problem for funnel varieties, so you want to know which funnel varieties admit Kähler-Einstein metric, then okay, let's look at dimension. Well, dimension one, this is just the only funnel curve is the Riemann sphere, and there we know that it has a metric with constant curvature. Now for dimension two, there are 10 deformation families of funnel surfaces, and in the 80s and early 90s, so people were very much studying this problem, and then Thiam and Yau, so this is actually many papers, they classified which funnel surfaces admit a Kähler-Einstein metric. So basically there are these 10 deformation families, and for eight of them, they admit Kähler-Einstein metrics, and for 2 of them, they do not have a Kähler-Einstein metric. And as I said, this was very analytic. So the last paper for the classification is a paper of Thiam and Bernationes that is over 17 pages. So this is really serious and deep analysis. And so if you now try to go to dimension 3, there are 105 deformation families of funnel threefolds, and at that time it seemed completely unreachable to have a similar classification of Kähler-Einstein funnel threefolds. However, very recently in 2015 we have a big result. So this is this was proved by Chen, Donaldson's son, and Tian, they proved that funnel manifold admits a Kähler-Einstein metric if and only if X is K polystable. So today I will not define what the K polystable means. I will do this tomorrow. But what you should think about this is that if X admits admitting a Kähler-Einstein matrix is an analytic condition, and K's polystability is an algebraic subcondition. So it's quite remarkable that the existence of Kähler-Einstein metric turns out to be an algebraic question for manifolds. And then starting here, algebraic geometers started to investigate this notion. And in January 2020, there was this conference at AIM, which was called K stability and related topics, where people got together to study this notion. And in this I was participating in this conference, and then in this conference in the afternoons, people were divided into groups to try to solve some problem. And then Vanya Chelstov proposed that one of the groups that got together to solve the Calabi problem for funnel prefix. And so this was very exciting, and actually we started working on it on this conference. And this was more or less when the pandemic started. And so we worked on it for the whole first year of the pandemic. And then finally we sort of completed the project roughly 1 year later. And so this is a sort of a classification of funnel prefolds that admit Kähler-Einstein. So this is not a complete classification in the sense that in dimension 3, some new phenomena occur. So as we saw for surfaces, there were 10 deformation families, and for each one, the answer was either yes or no. So either all the members of that family had a Kähler-Einstein matrix, or no member of the family has a Kähler-Einstein matrix. So in dimension 3, things are different. So it's very well known that there are some families. There is the famous V22, for which some members admit Kähler-Einstein matrix and others don't. So what we actually prove is that we prove for each of the 105 deformation families, we decided whether the general member admits a Kähler-Einstein matrix or not. And so this is the funnel team, and you see their names on the next slide. And so we finished it, and really by looking at using this new available tools coming from birational geometry to attack the problem. And so basically we went one by one at the families, and in the end we could not actually have a paper with the results because it was too big. So we actually wrote a book. And so this is coming out soon. So this is the list of the funnel team. Myself, Ana Maria Castravec, Vanya Chelstov, Kento Fujita, Anne-Sophie Colagiros, Jesus Martinez Garcia, Konstantin Shramov, Hendrik Soos, and Nivedita Tifana. And so tomorrow, what I plan to do is to go into explain a bit more about what is the minimal model program and the tools from birational geometry that we used to prove this theorem. So thank you very much for your attention.